So, as was said before, the first thing that happens at the nephron is filtration. It's the creation of filtrate, which is basically blood plasma minus any of the proteins or formed elements that are found in the plasma. Those are filtered out and they're kept in the blood. What exits the blood and goes into Bowman's capsule is referred to as filtrate. That's the stuff that we are reabsorbed from, and the remaining part that's not reabsorbed can have a little bit of secretion into, and then that's as it exits the nephron, that's urine. So the first step, excuse me, the first step is filtration. And so the membrane that causes the filtration. So basically the paper of the coffee maker, there's the filter basket and the coffee pot, and the membrane that keeps the coffee grounds in and lets the coffee through is the filtration membrane. So it consists of the fenestrated glomerular capillaries, which is so it's an endothelium with small holes in it that allows liquid to pass through. It's the visceral part of the glomerular capsule, so that's the podocytes that surround each one. And it's the basal lamina of those two epithelial layers joined together. So it kind of is a gel-like substance. And the liquid has to pass through it. So it ends up looking like this. The podocytes wrap around the capillaries and they leave little slits called filtration slits. And the capillaries, you can see the fenestrations in the capillaries here, and the liquid comes out in the strips between the podocytes. This allows for the passage of water and small solutes. Plasma proteins don't make it in it, neither do blood cells. There's a negative charge that also helps repel the proteins, but that's really neither here nor there. It's basically the holes are small. So it's really a semi-permeable membrane, as it were. There are cells, the mesangial cells that can engulf any macromolecules to get through, but we shan't worry too much about that. It basically looks like this. The blood plasma is here, the blood's on this side. There's a fenestration between the epithelial cells. There's the podocyte here, and there's the basement membrane here. So liquid has to pass through these three parts. And the thickness of it and the size of the pores really are major factors in how much filtrate gets produced. That plus the hydrostatic pressure, the blood pressure in here, and osmotic pressures and things that draw back really control how much filtrate is formed. So when we look at this, we're dealing here with 60 times a day. Every drop of blood passes through this. Every drop of plasma happens a lot, 60 times in a day. 99% of that plasma, that filtrate, gets reabsorbed, and so that we only end up creating less than 1% of the filtrate is urine, and that has the metabolic rate waste in it. We produce 180 liters of filtrate in the course of a day. And when you think about that, there's only 5 liters of blood, and somehow we filter it numerous enough times that we produce 180 liters of filtrate, which is about 45 gallons. It's the size of a big oil drum. And we produce, a liter of urine, liter and a half of urine. So most of it gets reabsorbed. The filtration is that first step. Reabsorption is probably the more important step. It's the bigger step. Filtration is a very simple thing. It just is some pressures and some holes, and the liquids leak out. The reabsorption is returning back to the blood that which we want to keep. So all the nutrients, glucose, the amino acids, most of the water, a lot of the salts, a lot of the sodium, other components that we want to keep. Now the third process is called tubular secretion, and this is the reverse of absorption, and this is an addition to the urine. It's getting rid of stuff that we want to get rid of that maybe got reabsorbed. So it was filtered out, reabsorbed, but there's too much of it, so we put it back in the urine with secretion. Potassium is the big thing for this. So fundamentally it looks like this. Blood comes in, it's filtered out here, filtrate is formed, reabsorption happens back into the bloodstream here, all the stuff and most of the water, a little bit of stuff like excess potassium gets secreted back into the filtrate, and that's what is expelled from the body as urine. So like I said, filtration, it's passive. It's driven by the pressures, the pressure differences. It's a filter, so that's why it's called filtration. There's a huge surface area, and there's many glomeruli in each kidney. There's over 1 million in each kidney, so there's a huge amount of surface area. The blood pressure is a little bit higher than in other capillaries, just because of the nature of the branching of the and the diameter, so there's a little less resistance going there. And anything that's larger than the filtration slits is kept in the blood, and so there's osmotic pressure is maintained, the same as when we looked at the cardiovascular system. So we look at the pressures that are involved with creating the filtrate. So this is net filtration pressure, and it's the exact same as when we looked at the bulk flow in normal capillaries. There is a hydrostatic pressure, glomerular hydrostatic pressure, which is really the blood pressure in the glomerulus. We called it capillary hydrostatic pressure before. It's the same thing. It's blood pressure. What opposes that is the colloidal pressure, colloidal osmotic pressure, sucking liquid back by osmosis into the capillaries, and this capsular hydrostatic pressure, and that's really how much filtrate is in the capsule. If there's a blockage in the renal tubules, then this capsular hydrostatic pressure goes up, and then that filtration pressure goes down. So really, it's the force pushing out here, which is in purple, minus the force pushing back in, which is the capsular hydrostatic pressure, and the osmotic pressure, which is in green here. So it's basically 55 pushing out, 15 pushing back, and 30 sucking back by osmosis, so that we end up with a net filtration pressure of about 10. Now, in people that have too high a blood sugar, then maybe we've got too much colloidal osmotic pressure, or people that like have hyperproteinemia will have less filtration pressure because there's too high an osmotic pressure. People with low blood pressure, like say somebody that's hemorrhaged, the blood pressure is too low, then the glomerular hydrostatic pressure goes down, and filtration pressure, so the kidneys basically shut down. People with blockages, the filtrate backs up, and the capsular hydrostatic pressure goes way up, which reduces this as well. And so these are all things that can cause kidney malfunction. Really, we want filtrate to be formed at a very steady rate. And we call this filtration rate the GFR, glomerular filtration rate. And it's really supposed to be about 120 to 125 milliliters per minute. So it should take you about 4 minutes to fill a normal water bottle with filtrate. So what governs this and what keeps this steady is the net filtration pressure, the permeability of the membrane, and the total surface area available for filtration. And the one that we can regulate is the net filtration pressure. Total surface area changes over time. Like if somebody was to have a kidney removed, obviously the total surface area would be cut in half. The permeability of the filtration membrane happens in various diseases. Some autoimmune diseases make the filtration membrane more permeable. Some things, so that would be a nephrosis. Other things make it less permeable, so that would be inflammation of that membrane. So a nephritis will make it less permeable. And in order to maintain the GFR, then we have to screw around with the net filtration pressure. So we control this with different mechanisms. So intrinsically, we've already talked about it. This is the juxtaglomerular apparatus. So this is auto-regulation, and it's acting locally at the kidneys. There's an extrinsic control, which is basically hormones and nerves that affect blood pressure. The idea is to control blood pressure, but by controlling blood pressure, you will affect the kidneys. So it's not directly associated with trying to control GFR. So the intrinsic controls, as long as your blood pressure is about right, we basically control it with this juxtaglomerular apparatus, where if filtrate is being produced too quickly, the distal convoluted tubule gets stretched and dilates, which then inhibits and causes vasoconstriction in the afferent arteriole, which then lowers the blood pressure and reduces the GFR. If there's not enough filtrate being formed, then the juxtaglomerular apparatus senses it, causes dilation of the arterioles, which then increases the net filtration pressure, which then increases the filtration rate. Now, this is an automatic thing. It happens in the kidneys, and this is one of the reasons why you can transplant a kidney, because the kidney takes care of itself for the most part. Now, there's also a myogenic mechanism, and I'll just briefly mention it, but basically, if your blood pressure spikes, like all of a sudden, because say you've had a fright, um, and your blood pressure goes way up very quickly, then what happens is that surge of blood pressure comes down, stretches the walls of the arteriole, which then contract in response because smooth muscle contracts when it's stretched, and that contraction moderates that spike in blood pressure and maintains the GFR correctly. So that's what this is saying, that increased blood pressure. And it's very straightforward. The tubules, look at it. Now, on top of the stretch, there's also the amount of salt gets looked at. So, because if things are moving too quickly, if the GFR is too high, then you won't reabsorb enough sodium, and the juxtaglomerular apparatus notices that. In the intrinsic control, sympathetics are very much at work here. So normally the renal blood vessels are dilated and the autoregulation prevails. But if you end up sympathetic under stress, then what happens is norepinephrine is released, and epinephrine by the adrenal glands. It causes constriction of the afferent arterioles. It inhibits filtration, and it actually causes you to then release renin, which then causes angiotensin to increase blood pressure. And all of this stuff is to maintain blood pressure in a fight or flight situation. Basically, it scares the piss out of you, as it were. You produce less urine when you're under stress. So we will talk, we've talked last semester about the effects of angiotensin and its effect on blood pressure. But the effect on blood pressure is that it causes the changes in the kidneys that cause less production of urine. So all of these things just work together. Prostaglandins affect GFR, and other chemicals affect GFR as well.